Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Monday, November 30th, 2020, which is our scheduled 69th day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do nows and see what our schedule is for today. No new papers to pick up today. Remember when we left last Wednesday? By the way, hope everyone enjoyed their Thanksgiving break. I certainly know I did. Was percent comp, empirical formula, and true molecular formula. Problem one only. So there were 6 problems to do associated with problem one over percent composition. You were to do those problems only. So hang on to your assignment. Of course, you can check. We're not done with it yet. We'll finish it up today. But you can, of course, check the work you did on problem one if you're here in school, either on the board in the back or you're at home on the answer keys page in Canvas. I have it posted there as well. So today we're going to finish up the Unit 6.1 notes packet on the mole. Today we're going to learn how to calculate an empirical formula and a molecular formula, which in many cases is also called the true molecular formula. You'll finish your current homework assignment, and that will be due tomorrow. I'll be collecting it, by the way. We also have a lab tomorrow, and we have an exam, as I mentioned last week. We have an exam coming up this Thursday. So study list will be posted in Canvas tomorrow, all right? You also have a mastering assignment that is due tomorrow, December 1st. Can't believe it's December already. By 7:30 a.m. And of course, hopefully you worked on that some over the long weekend. You should have been able to do a great majority of it, except for the last several problems, which involve what we're going to go over today. And again, note to self, always show work and label round correctly, of course, when doing any kind of computational problems, which this Unit 6.1 was certainly full of those types of problems. But this was an all-math unit, if there ever was one. All right. Okay, well, let's pull up our lesson and get to it. So we're going to talk about an empirical formula today, an empirical formula, which is the lowest whole number ratio of the moles of elements in a compound. So it comes from the mole, just as percent composition does as well. Remember, we use molar mass in determining percent composition. We determine empirical formula if we know, number one, the percent composition of the compound that we're talking about, or if we know the mass of each reactant that forms that compound. Either way, we can determine its empirical formula by the following these steps. Number one, convert the percentage or mass of each reactant to moles by dividing by its molar mass. All right? So let's think about that. By dividing by its molar mass. So let's say we have X number of grams of a substance, and we put that over 1, all right? And we want to convert this to moles. Okay, we've done that. We did that back in the second lesson in this unit, all right? So we would take 1 mole of that substance. Let's see, this is substance A, all right? 1 mole of A over its molar mass in grams, all right, of A. And their grams of A would then cancel, all right, which then would leave you with X number of moles of A, all right? So think about mathematically what we did. We took its mass right here initially, and we divided by its molar mass. So then the moles, in a little shortcut type equation, is equal to the mass of a substance divided by its molar mass, all right? And so that's where this comes from right here. Secondly, divide the number of moles of each element by the smallest number of moles that you have. Okay, this is going to get us to a percentage. All right, this is going to get us to a percentage. All right, or a decimal, or fraction. If all answers are not whole numbers, then multiply each element's number of moles by the lowest whole number that will convert all decimals to whole numbers. All right. So for instance, let's say if we get 0.5. Well, we can't have 0.5 in a formula. All right. Remember, there is no such thing as S2O2.5. All right. There is no such thing. Remember, elements combine in whole number ratios. Dalton, remember him? And so we're going to have to get those fractional numbers of moles to whole numbers. And we'll do that by multiplying by the smallest whole number we can use to do that. We may or may not need to do this, step 3. It's possible we don't need to do it. All right, well, we'll see. All right. So I also said up here, we can convert the percentage or mass of each reactant. Okay, so remember, percent composition is a percent by mass. All right, so if the percent composition of something is 25%, or the mass percent of a particular element is 25%, well, what that means is in a 100-gram sample, there's 25 grams out of 100 grams. So, I mean, it's percent composition or percent by mass is via mass, all right? Okay, so then we can use either the percent composition or the actual mass of the reactant to do step 1. So I wanted to make sure you're aware of that. All right, so let's go on to the examples, and I'll show you how to work this thing out. So this first one, what is the empirical formula of an unknown compound that is composed of 25.90% nitrogen and 74.10% oxygen? And then it says name it. All right, name it too. All right, so we have 2 elements in this compound, N and O. All right, so the first step is we're going to take its mass or percentage, in this case we have percentage, and divide it by its molar mass. All right, so nitrogen we'll use 25.90. You don't even have to convert it back to a decimal. You can leave it as a percentage, all right, because whether it's 25.90 or 0.2590, when we divide and get a ratio, the ratio is going to be the same regardless, all right, so you just leave it. Nitrogen's molar mass is 14, all right, so we're taking its percentage, which is its mass, all right, mass of 100 grams, and divide that by its molar mass, and that'll give us a number of moles, all right. 1.850. I left this at 4 decimal places, or 4 sig figs, or sorry, 3 decimal places, which is 4 sig figs, the same as the number of sig figs there. Because again, when you're dividing by molar mass, that's a constant. We don't determine sig figs by that. So we just round it off at 4, all right? We don't have to extend it on out. And because we're going to get a ratio. So we get 1.850. The second one, 74.10, oxygen's molar mass is 16, and that would give us 4.631 moles. So again, I'm leaving it at 4 sig figs. Okay, now, second step, divide the number of moles you have of each divided by the smallest number. This will get us to a ratio, all right? Well, the smaller of those two is 1.850. And so we're going to divide them both by 1.850. And again, I'm going to leave this at, well, of course, that's 1, all right? So now, does this get us a whole number? Well, actually not. It gets us right at about 2.5, all right? So if we were to stop right here, our formula would be NO 2.5, no can do, all right? So we want to multiply that by the smallest whole number. That'll get us to a whole number. Well, if you take a 0.5, what do you multiply it by to get it to a whole number? And the answer is 2. All right. So we're going to multiply both of these by 2. We got to keep the ratio between the two the same. So we're not just going to multiply the one by 2. We're going to multiply them both by 2. All right. So think about that. Just to make sure you understand, we want to keep the ratio the same. So now the ratio is 2 to 5, or 2 and 5, all right? So that then translates to an empirical formula of N2O5, all right? And if we're naming that thing, this is a molecular compound, covalent bonding, so we need prefixes, dinitrogen pentaoxide or pentoxide if you drop the A. All right. All right. So let's think about this multiply business here. Again, an empirical formula is the lowest whole number ratio. All right, whole number. So if we do this second step here and our answers are both whole numbers, we're done. But if not, then we've got to multiply by a small whole number in order to get that fractional number of moles to a whole number. So we said with a 0.5, I'll write out here. So if it's a 0.5, we multiply by 2. All right. If we get something around a third or 0.3 repeating, then we multiply by 3, right? Because a third times 3 is 1. If we get something like 0.25, then we multiply by 4. All right, by 4. 0.25 times 4 is 1, a whole number. If we have like a 0.2, then we multiply it by 5. All right. If we have a 0.16 repeating, I'm just thinking of my common fractions here. That's 1/6 actually. You multiply it by 6 and so on. This thing has to be very, very close to a whole number in order to not multiply it by something. All right. Now, if it's 0.1 or something or less than that, then it's fine. But, you get upwards of 0.2 or whatnot, you can't do that. All right. You got to be more specific. All right. All right. Second one, what's the empirical formula of an unknown compound that is formed when 9.030 grams of magnesium combines completely with 3.480 grams of nitrogen? Again, we're going to name it too. So this one, we have Mg and N. Instead of being given percentages, we're being given masses. Well, the procedure is exactly the same. We're going to take the mass of magnesium and divide it by magnesium's molar mass, which is 24. All right. We're going to take nitrogen's mass, 3.480, divided by nitrogen's molar mass, which is 14. All right. So here we get 0.3763 moles. Again, I'm sticking with the same number of sacates I've got up here. And the second one, I get 0.2486 moles. Mass divided by molar mass equals moles. All right. So we divide both of those by the smallest number, 0.2486. And again, the bottom one is 1, of course. And the top one comes out right at around 1.5. All right, so here again, not a whole number, certainly not close enough to a whole number to round it up to a whole number. So again, we'll multiply both of these by 2. We get 3 to 2 ratio, Mg3 and 2. And that, of course, is an ionic compound formed from ionic bonding, metal, non-metal, so no prefixes here. This would just be magnesium nitride. Magnesium nitride. All right. All right, third one. What's the empirical formula of an unknown compound that is 42.90% carbon and 57.10% oxygen? All right, so we have carbon and oxygen. 42 point, again, we have percentages here, but they're percentages by mass, so we can just use those as if they were a mass, okay? A carbon will divide by 12, oxygen by 16. 3.575 moles for carbon and 3.569 moles for oxygen. So we're going to divide very close to those two. We'll divide by the smaller of the two, 3.569. Of course, the bottom one is exactly 1, and the top one, do a little double checking here. 3.575 divided by 3.569. 1.001. 0.17. Well, you know what, folks? That's close enough to 1 for me. And so we're just going to leave that right there. So these are both whole numbers after step 2, which means step 3, multiplying by some whole number, is not necessary. And so it's just one of each, which is CO. And again, that's a molecular compound, so we would use prefixes. This would be carbon monoxide. Remember, we don't use mono. There's only one in the first element. We just use the first element's name, carbon monoxide. All right? So that's empirical formula. Take the percentage or the mass that you are given, divide each of those by that element's molar mass. That'll get you moles. Step 2, divide all the moles by the smallest number of moles. That'll get you a ratio. All right? Now, if after step 2, all your answers are whole numbers, you're done, just like we were right here. But if they're not, and you have, a decimal point, then you're going to need to multiply by some small whole number, like we wrote about here, to get you to whole numbers and a whole number ratio, because that's what empirical formula is, the lowest whole number ratio of elements in a compound. And again, elements or compounds are formed by elements combining in whole number ratios, okay? All right, next, molecular formula or true molecular formula. Let's look at that. Okay. So the molecular formula or true molecular formula of a compound is either the same as its experimentally determined empirical formula, that could be it, or if it's not, it would be a whole number ratio of an empirical formula. So here's what I mean by that. So here are two compounds, two organic compounds, ethine and benzene, all right? Ethine, of course, is a alkyne. Benzene, of course, remember, is an aromatic hydrocarbon. Remember, it's in the ring structure. And if you look at those two formulas, C2H2 and C6H6 for benzene, all right, both of those have carbon and hydrogen in the same ratio, because 2 to 2 and 6 to 6 are both 1 to 1, right? If you reduce them, all right? And so both have the same empirical formula, which is CH. That's the lowest whole number ratio between carbon and hydrogen in both of those. Like I said, 2 to 2 or 6 to 6 both reduce to 1 to 1. And so the molar mass of CH, the empirical formula, is 13, 12 and 1. The molar mass of ethine, C2H2, is double that, 26, hence 2 to 2. And of benzene is 6 times 13, or 78, okay? So both of those share the same empirical formula, okay? Now, let's talk about, again, what types of formulas are empirical and what types are not before we move on, all right? Because, again, empirical formula is the lowest whole number ratio. Neither one of those is the lowest whole number ratio. It's a multiple of a whole number ratio. Remember, the lowest whole number ratio was 1 to 1. That's why both of those share the same empirical formula, CH. All right, so let's look at that a little bit more closely. So here are some true molecular formulas, all right, that are also empirical. All right, sodium phosphate, Na3PO4, all right, potassium chromate, K2CrO4, nitrogen dioxide, NO2, barium sulfate, BaSO4. So these are actual formulas, molecular formulas, that are also empirical. Here's what I mean by that. What's the lowest whole number ratio, or what's the whole number ratio involved in this first one? 3. Sodium is 3, Phosphorus 1, oxygen 4, 3 to 1 to 4. Can that be reduced any further? No, can't. Can't. K2CrO4, 2 to 1 to 4. You say, well, we could reduce 2 and 4 by 2, but if you divide the Cr, which is 1 by 2, you get 0.5. That's not a whole number. NO2, same thing. BaSO4, same thing. Those true molecular formulas are also empirical, all right? Then we have true molecular formulas that are not empirical. Well, we had two of them over here, C2H2 and C6H6. Here's one, glucose, C6H12O6. That's a true formula for glucose, but is that formula empirical? And the answer to that is no, it's not, all right? If we reduce that down, we divide it by 6, we get CH2O, all right? That's the empirical formula of glucose. Glucose's actual molecular formula, or true molecular formula, is 6 times that empirical formula. All right, here's one. P4O10, tetraphosphorus decaoxide, or decoxide. Is that formula also empirical? And the answer is no. The empirical formula for that compound is P2O5. Its actual molecular formula, or true molecular formula, though, is P4O10, which is twice its empirical formula. About ethane, C2H6. Is that formula empirical? The answer is no, it is not. Ethane's empirical formula is CH3, but its true molecular formula, of course, is C2H6. And here's another one. Dinitrogen tetrahydride, N2H4. Is that formula? That is its formula. That's its true molecular formula. But is that formula empirical? No, it's not, because that can be reduced by 2. Its empirical formula is NH2. So that's what I'm referring to here. So the true molecular formula of a compound, its actual formula, could also, be its empirical formula, or if it's not, then it is some whole number multiple of an empirical formula, okay? We can determine the true molecular formula of a compound by knowing the following information. Number 1, we need to know its empirical formula. Number 2, we need to know the empirical formula's molar mass, which we can calculate quite easily. And then number 3, we're going to compare that to the compound's true molar mass, its actual molar mass, and then we'll get it from there, okay? So let me raise this up a little bit. Okay. So the empirical formula of an unknown compound is CH4N. So that's its empirical formula, all right? If its true molar mass is 60 grams per mole, then what is the compound's true molecular formula, all right? All right, so here's what we need to know. So here are the steps, all right? So let's review the steps. Step 1, find its empirical formula. Step 2, find the empirical formula's molar mass. Step 3, take the true molecular formula's molar mass divided by the empirical formula's molar mass, and see what that whole number ratio is. Or is it 1? If it's 1, then the true molecular formula and the empirical formula are the same. If it's not a whole number, if it's a whole number other than 1, then the 4th step then is to take that whole number times the empirical formula, and that will then get us its true molecular formula. So basically we have 4 steps we're going to look at here. Now here we're given the empirical formula. We already have it, so we don't have to find it. It's already done, all right? So that step's already over. Find the empirical formula's molar mass, all right? So we have our empirical formula here is CH4N. So C is 12, H is 4, and N is 14, 30 grams per mole. Third, our true molar mass is given 60, all right? So let's take 60 over 30, the empirical formula is molar mass, and we get a whole number of 2, all right? 2. So this compound's true formula is twice that of its empirical formula. So that would then mean then its true molecular formula would be 2 times its empirical formula, which would be 2 times CH4N, which then would be C2H8N2. All right, C2H8N2. All right, last one. A compound is composed of 58.80% carbon, 9.80% hydrogen, 31.40% oxygen. If its true molar mass is 306, then what is its true molecular formula? All right, well, we need to find its empirical formula. Here we don't have it, so we're going to determine it. All right, so we just looked at that a few minutes ago. How do we get empirical formula from percent composition? All right, so we got CH and O. Our carbon percentage is 58.80. We're going to divide that by carbon's molar mass, 12. All right. Hydrogen, 9.80 divided by its molar mass, which is 1. That's easy enough. Oxygen, 31.40% divided by its molar mass, 16. So here we have 4.900 moles. I'm sticking with the sig figs there. Here we have 9.80 moles. And down below we have 1.963 moles. What do we do next to get empirical formula? We divide all the moles by the smallest number of moles, which in this case is 1.963. The bottom one, of course, is 1. The middle one actually comes out right at around 5, very close. And the top one comes out at right at around 2.5. Again, that is not close enough to 3 to round it, so we're going to have to multiply by a small whole number, which of course 0.5 we said would be 2. So we multiply them all by 2 because we got to keep the ratio the same. So this is 5 carbons, 10 hydrogen, and 2 oxygen. So our empirical formula is C5H10O2. All right? So that is our empirical formula. We're trying to find true molecular formula. So we've got the empirical formula. Now we need to find that empirical formula's molar mass. C5 would be 12 times 5 is 60, 10 for hydrogen, 32 for oxygen, 102 grams per mole for the empirical formula. All right, now we're going to compare our true molecular formula to our empirical formula. Are they the same? Well, no, they're not. Now, if that said, that 306 said 102, and that the empirical formula is 102, then we have a situation where the true molecular formula and the empirical formula are one and the same, and that is the case sometimes. It's not here. All right, so here, then if we take that 306 molar mass divided by empirical formula's molar mass, which is 102, we get 3. All right, and so the true molecular formula then would be 3 times the empirical formula, which would then be C15H30O6. C15H30O6. All right. Well, I think that takes care of today's lesson. So on your assignment that you began last Wednesday, Remember, you were only to do problem 1 regarding percent composition. Now, after having done this lesson, you should be able to finish that assignment. And again, I'll be collecting that assignment tomorrow. All right, so tomorrow we're going to have a lab over percent composition and empirical formula. And then I'm also going to hand out the review for our exam. Remember, you got a mastering due tomorrow as well. You'll be able to finish that now too. And we have an exam coming up on Thursday. I'll hand out the review tomorrow. I'll post the study list in Canvas tomorrow. Wednesday will be a review day and then or a work day as well. And Thursday, then we have an exam. So I think that's it for today. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe. Keep working hard and stay focused. And I'll catch you all next time. So long.